Good morning, everyone. Welcome to the session about ExtremeEarth, a project that for the last 3 years has studied the application of big data and AI techniques and technologies to Copernicus data. Together,
recording in progress.
In our session, we have myself, Manolis Koubarakis. I'm a professor at the University of Athens. We also have my colleague Florian Appel from the company Vista, a geoinformation company in Munich, in Germany. And we also have Nick Hughes, the leader of the ice service of the Meteorological Institute of Norway. The three of us will present to you some of the achievements of the ExtremeEarth project. And I will go first with a short introduction to the ExtremeEarth project. And then Nick and Florian, or rather Florian and Nick in that order, will present to you what we have achieved in the two use cases of the project, the food security use case and the polar use case. So let me start by presenting to you the whole set of achievements of our project. So when we proposed ExtremeEarth back in 2018, we promised to go beyond the state of the art and develop artificial intelligence and big data techniques and technologies that scale to the petabytes of big Copernicus data, information, and knowledge, and apply these technologies in two use cases, the food security use case and the polar use case, that would have been done in collaboration with the food security and the polar thematic exploitation platforms that have been created by the European Space Agency. In our project, we will also be extending the HopsWorks data-intensive AI platform that has been marketed by our partner Logical Clocks, with the intention to offer unprecedented scalability to extreme data volumes and scale out distributed deep learning for Copernicus data. Everything that we have developed runs on Creo Dias, and with the exception of commercial software, the rest is open source, so that it can be adopted by the strong European Earth observation downstream services industry. A significant part of our project is about linked geospatial data systems, and we have basically extended systems that we already had when the project started, and we made sure that these systems scale to the extreme volumes of Copernicus data. More details in a minute. Our consortium consists of 11 partners. We are a mix of universities, research centers, and commercial companies, commercial organizations. And we are a mix of participants from computer science and remote sensing. From computer science, we have the National and Kapodistrian University of Athens, my university. We have KTH from Sweden, and we also have Demokritos, a research center in Athens, and also Logical Clocks. From the remote sensing area, we have the University of Tromsø, the University of Trento, the Meteorological Institute of Norway, British Antarctic Survey, Polar View, and also Vista. Vista and Polar View and Logical Clocks are the companies in our consortium. Now I will present to you our key technical achievements, and I will start with the use cases. Our first use case is the food security use case. And in that use case, we are developing irrigation recommendations for farmers, essentially high-resolution water availability maps for agricultural areas in the Danube and Duero catchments in Europe. This is work done by our colleagues at Vista and the University of Trento, and this is the use case that my colleague Florian will present to you in the next presentation. Our second use case is the polar use case, a use case located, let's say, in the Arctic region. And for that use case, in that use case, we have produced high-resolution sea ice charts using massive volumes of heterogeneous Copernicus data. And these ice charts are of value to organizations that are working in the Arctic region, including the Arctic communities. So this is a use case that has a lot of societal impact. The use case has been implemented under the lead of the Meteorological Institute of Norway. As I already said, Nick Hughes is with us here today, and he will present the use case. Also, British Antarctic Survey played a big role, also Polar View, and also the University of Tromsø. A very important contribution of our project is the development of scalable deep learning techniques for Copernicus big data. In more detail, we had two important contributions. One contribution for the food security use case, where we developed LSTM deep neural networks for crop type mapping using Sentinel-2 data. And one contribution in the polar use case, where we actually developed a very big selection of interesting deep neural network architectures, this time for sea ice classification using Sentinel-1 data. The partners that developed these deep neural networks were the University of Trento for the food security use case, and the University of Tromsø, DLR, and KTH for the polar use case. Since we have been developing deep neural network architectures, as you know, we would need very large training data sets, and a lot of the research in the project has been devoted to developing such very large data sets. The first data set that we developed has been based on 16 Sentinel-2 images located in Austria. It's a very big data set consisting of about 1 million pixels, and every pixel is labeled with one of 13 crop types. And this data set was used to train the LSTM networks that we developed in the food security use case. By the way, all the data sets that I will present are available on our website and also on Zenodo. So they are made public for the whole community, for the whole remote sensing community interested in these problems to be able to use them profitably in the future. Our second data set has been for the polar use case. And here we have used 30 Sentinel-1 images. And the data set consists of patches of these images, where each patch is labeled with one of 6 ice types. And we use this data set to train some of the CNN networks that have been developed for the polar use case. This is work done by the University of Tromsø, the LSTM networks, the dataset for the LSTM networks that I presented earlier were done by the University of Trento and our colleagues at Vista. Going on, our partner DLR has developed 2 other training datasets, again based on Sentinel-1 images, again for sea ice classification, using this time techniques like latent Dirichlet allocation and active layer. Finally, in the dataset area, our colleagues from the Meteorological Institute of Norway used 12 Sentinel-1 images to develop a dataset with 2 classes. Each patch is labeled with 2 classes, ice or water, but also with information about sea ice concentration, ice type and form, and this is has been proven out to be a very important data set for the training of the CNET networks of the polar use case. So this covers the dimension of deep learning of the project. Now we come to the other very interesting dimension of our project, the linked geospatial data systems. In this area, we have developed 4 systems. Basically, all these systems were extensions of systems that we already had. The first system is called GeoTriple-Spark. It is about transforming big geospatial data from their legacy formats, for example, a shapefile, into RDF, okay? And we have shown that GeoTriple-Spark can scale to very large amounts of data, to terabytes of data. We also developed Jedi Spatial. Jedi Spatial takes data sets that have been produced by GeoTriple-Spark and interlinks them with other interesting geospatial data. So it's an interlinking tool. And again, we have shown that it scales to big data. We have also developed Strabo 2, a system for querying big linked geospatial data using the OGC standard GeoSpark. And again, we have shown that it scales to big data. Finally, we have developed the system SemaGrow, which is a system for federating linked geospatial data sources. And we have also used that it can deal with many endpoints, and it can scale to large amounts of data. All this work has been done by my group in Athens and the group of Democritos in Athens as well, where, by the way, we have an excellent sunny weather today. I hope the same is true in the place where you live. Last but not least, all the technologies that we developed in the project have been developed in the context of the ExtremeEarth platform. Being a good European project, we also developed a platform. And our platform is based on HopsWorks, the system, the data and AI system of logical clocks. And logical clocks, together with KTH, have developed this platform, which runs on HopsWorks. So all of our systems run on this platform, which runs on HopsWorks, which runs on CreoDias, and this is how we bring together Earth observation data, systems that work with it, and computational power, so that we can develop applications. And what is important to stress here is that HopsWorks has been extended by logical clocks and KTH with appropriate functionality. So now it is not only one of the best data-intensive AI platforms in Europe, but probably the only one of that kind that can also deal with Earth observation data. And several extensions were done, like the file system, the resource scheduler, the metadata and security model, the feature store, and so on. So this is what I wanted to say in a high-level way about our project. If you want to learn more, please join us next Thursday for a full-day workshop where we present the achievements of ExtremeEarth to a wide audience. All the information about the workshop is on our website. Notice that our website is earthanalytics.eu. Okay, so don't miss us. Please follow us also on Twitter if you want to learn more about our project. Our project finishes this month, but we still have a lot of interesting things to report. So join us, and with this, I stop and I give the floor to my colleague Florian to present to you the food security use case. Thank you very much.
Yes, hello. My name is Florian Appel. I'm working for Vista. I will present my slides in a minute. Let's go. I think you should see them now. So, yes. Welcome from Munich, or a little bit outside of Munich. My name is Florian Appel. I'm working for Vista since more than 20 years now. I started from geography and Earth observation, and have a good story in the last years on how Earth observation and data techniques evolved to more and more applications. So the food security use case is named here: big data, deep learning, hydrological and crop modeling for food security, with some examples from the Danube. The presented work is together with my colleagues at Vista, and of course the colleagues from the University of Trento, who did a lot of the crop science and things. Let's switch to the next slide. Here we go. Some short words about Vista. We are a SME company, or former SME company. Now we belong to a larger company, the BayWa, which is an agricultural trade organization in Munich, Bavaria. So we are working on Earth observation and modeling since 95. Our background is doing applications for the users and customers out of research and development activities. And we have a blue branch, the hydrology, and we have a green branch, which is the agriculture. In this project, they fit nicely together. So we are running snow monitoring and runoff forecasting, also hydropower productions. We are doing services for precision farming, including yield forecast, irrigation management, and so on. And our brands, for example, are SnowSense, the food security tab, Talking Fields, and Ypsilon, the yield prediction by satellite. But going to the food security use case, some background, but everyone knows about that food security is one of the most challenging things in the moment. We have a change in climate, we have a changing population densities, we have population growth, we have changes in food consumption, and all that together requires, on the one hand, the biomass production, and so yield needs to be increased, that we are facing different risks of yield loss, so extreme events, making harm to the corn, to the maize, and all the yield around the world. We can face this on the technical side by fertilization and by irrigation, and of course improved management and improved seeds and all that. But here in the use case, we are concentrating on irrigation, since this is also a Vista story. And here we need information about the water resources and the availability of the water resources, a different kind where the water can come from to secure the yield. In Europe, large areas of the agricultural production areas receive water also from a storage from winter, so for example from the Alps or from the Pyrenean mountains. So our two catchments where we are working in this project are the Danube and the Duero. So here we combine snow storage in the winter and irrigation in summer. Yes. And our approach within ExtremeEarth is to produce, on the one hand, on the blue side, the information about the water availability. So, for example, water availability maps based on Earth observation and based on models. And on the green side, we have the information about the crops, the crop development, and from that, the water demand from the crops. So, and taking both sides and both information, we will generate, or we are generating information and maps to support the farmers in their decisions, but it's not only about farmers, it's also about other water management authorities, from local to continental scale. So there's the whole range of users, from farmers to governments, can achieve benefits from the results of this project. In the context of having such an approach with big data and Earth observation, we have structure in layers coming from the Copernicus data. So all the Sentinel satellites producing information day by day. The ICT layer from the CreoDeers, so the platform where data is stored, distributed, and computing power is available. The layer that is more specific on products in that context, the food security tab, is something that I will explain in more detail in the next minutes. Taking those computer facilities and data, we have activities in the project that's going from the Sentinel-1 processing, of course, the AI applications in the training in the context of the crop. And Manuel has mentioned the HopsWorks as one of the innovative tools that are working here. So coming from Copernicus, we are going through the crop information, and on top of crop information, the water availability and the irrigation information. This will come in the next slides in more detail and so on. Okay. Starting from my early sketch of when we set up the project together with the team, we had the idea of combining the blue side, the origin of the water, and the need of the water, using different processes on snow and land cover, different satellite resources, having a central connection, a model. So the simulation of, on the one hand, the water balance for the whole catchment, for the whole area, and on the other side, the high resolution simulation of the crop growth and the water they're demanding. And altogether, the story is from the seasonal water to the irrigation for the food production in one boat. So let me spend some words about Earth observation data and Earth observation processing. This is where we come from. I will not go to details on what satellite system is what delivering and what are the benefits, but there's a power of time series. And starting with the Sentinel-2 from Copernicus, we have a game changer in satellite applications. So we receive data several times a week yes, we have from these optical satellites, we have clouds, but we are able to cover the entire area of Germany within 2 weeks, and then it repeats again. So there's a constant data stream coming from the satellite and the European facilities to observe the land surface. So there's a power of time series, and time series, if you do some processing and image analysis and all that I will present later, you can retrieve the dynamics of the vegetation. And for example, here, it's the leaf area index, so it's the percentage of how much, or the portion of leaves towards the ground area. And so this is a parameter for the activity and for the from the plants. So this is something that Earth observation can nicely produce operationally. There's a lot of technical effort behind it, but that's the business companies like Vista or other organizations are doing. I mentioned the power of time series. Here we have more detailed view that you see that is high resolution, 10 meter to 20 meter. And you see here a sequence on an area north east of Munich. And you see locations for winter wheat. So here we have fields where winter wheat is growing. And with the analysis we do, we can provide information very dense about how the yield is developing there. And we can calculate also how much yield, how much tons per hectare of winter wheat can be harvested at the end of the season. To go there, the data, I mentioned that needs some processing. We have the high spatial and temporal resolution, but we have effects of the atmosphere. We need an atmospheric correction, so we need to exclude all the parameters we have from the atmosphere, so from the 800 kilometers of air and aerosols and clouds between the ground and the satellite. So our next level product is the bottom of atmosphere reflectance and the leaf area index. So these are directly observations as they are possible from inside or above the field. So we at Vista, we have a processing chain, and this chain is running also on the food security tab. So we are not downloading the data, we're using the data close to its origin and run the processors up there. Cloud classification, land surface classification, and retrieval of plant parameters like the mentioned leaf area index. So this is the standard of what we developed in the last 10 years and what is the basis of our daily work. But I mentioned having it not in our own facilities, but having it on the location where the data is. We started with an ESA project, or together with ESA, on establishing the food security tab. So there are several tabs around in Europe with the different thematic exploitation tab. Thematic exploitation platform means tab. So ours is dedicated to food security. So we are connecting the backbone of the Earth observation products, the tools and the methods, to a front end where we have data available, can connect the different users from the different communities, farmers, industry, agencies, scientists. This is so the whole bench with the data. So this is a platform where you can run processors, develop your own processors. So scientists and developers can go there and run it on the tab. And the tab has also function for sharing and for accounting and all that. And this is something that what we developed in the last years, and which is one of the bases for also the developments within ExtremeEarth. The tab has access to data sets, has tools, and has the solutions, as I mentioned before, on integration and service options and so on. This is something that is, on the one hand, now commercial, so users, customers can subscribe to their accounts to have the functionality, but there is also this option of sponsorship. So ESA is giving options on sponsoring that, and if you're a scientist and having a project, you can apply for a sponsorship that you can use the platform. There's a small proposal and there's a small report, but this is an excellent way on giving the users access to such thing like the tab. The tab itself is not only the technical platform, it's also in the center of the food, carbon, and water ecosystem cycle. So we see ourselves also as connector between the different branches and topics, and yeah, so it has a thematic orientation. Okay. Let's go to the crop type mapping. So this is something that was mentioned by Manolis as achievements of the tab, and crop type mapping is an important basis for all the services that are on top of that information. We have a complex service chain handling the training issues. So coming from training data, coming from Earth observation data, doing the large-scale training set, and all that important and complex things that are performed by the University of Athens. They have a lot of publications on that, and will not present much details here, but altogether it is based on the Sentinel-2 data, the image processing that we do at Vista and that we do on the food security tab, leading to time series. So I mentioned the time series, and out of that, and now on hops, we are able to derive the fields and derive the crop types for every season, because crops in that higher resolution area are changing. So this is a work which is requiring a lot of input data from Sentinel and a lot of training data, and so this is real big data in application. Click. So Vista was in charge of the processing on the tab for the areas for the different years in Europe. Trento generated the large training database, which is now available also from the project, with the 1 million of crop samples. And we intend to develop the deep learning system to perform this crop type mapping in different years and different areas. And as said, this is documented in publications and excellent scientific work. But also the next step is to make such achievements usable for the next generation of users, is something that we developed based on the trained models and based on the developments and adaptations of HOPSworks, which, as Manolis said, started as being not so able for Earth observation in the beginning, but is now prepared also for the spatial data, for the raster data, and all the specifications that Earth observation data is providing. The rough concept here is in the moment that the data expert, for example, is working on data that is processed on the food security tab, runs his training, doing his developments on HopsWorks, which is on the same platform, also on CryoDias. And if he has achieved models and results, he can deploy it on HopsWorks. And in the second step, on the right side, a user, yes, an expert user, but can use those trained models and can use additional data, new data on the tab from the satellites, combine the results from the trained models and from the freshly processed data, getting new products, for example, crop type maps, and has now the options, or has now the background for a new generation of services and new applications. This is something that we are strongly had in mind when we set up this. So what we had in the project as the processing chain is now on the food security tab, and yeah, this is a good achievement on how the science work and the big data work and the ICT work can be combined to results. The results in this first step are the crop maps. This is just a snapshot from the portal, and there's a transparency overlay, and this is not a perfect impression now for you on what a good crop map looks like, but this is nicely illustrating that all the terabytes of data that we have processed for generating the time series and generating this large area result in something simple but very important, the crop type map, as a basis for the next steps. Out of that, I will now give you some examples about the applications on that from the Danube. We mentioned that we are working in 2 European catchments, the Danube and the Douro. The Danube is a large one, ranging from the Alps down to the Black Sea, passing a couple of countries and a couple of landscape zones. And the Douro has also some specifications, being very, very dry, but very snowy in the north, and going and having a lot of reservoirs. So there are very good examples on all that technologies on Earth observation and modeling that needs to be applied within these 2 catchments. You see we have users involved where we are working with things. So the Danube River, as mentioned, from snow down to the Black Sea, a lot of agriculture and different groups of stakeholders there. What we did here and what I present now briefly is the crop mapping, the crop modeling, the water stress, and the irrigation. And for that, we have very abstract, again, a workflow, starting from the dense time series of Sentinel-2 images, including the already mentioned learning processes, resulting in a crop type map, and having this crop type map. And this is nothing that is there and will last for the next years. This is something that needs to be updated year by year, because the crops are changing, the rotation, the farming practice is all years are different. So there's a lot of data to be processed to have these crop type maps always up to date. This is information that for small areas and in direct context, the farmer is giving us. But if we want to run a service for a larger area, for a country, for a sub-catchment, This information is not available from the farmer, and here Earth observation is in charge to produce that. And with the developed things, we can go to this level. So having the crop type map as a basis, we apply our biophysical crop parameter model, and from that, we, for example, receive the crop water demand. I will show you the examples in the next slide. And in the end of this story, we see the effects on the yield and the potential and the results from irrigation. So how to do that? How to go from a crop map and to information, subnational information about water and yield. We are selected millions of pixels. So this is just a subset of the Danube area, in an area around Austria and Czech Republic, Slovakia, and Hungary. So 4.2 million pixels have been selected. Those pixels are representing most of the crops and most of the distribution of the crops. For each of this pixel, we have information from the satellite, the leaf area index, with all its varieties. So a lot of information. First, crop from the satellite, and second, also the actual state of the crop from the satellite, and combining those and the model in the background, which is driven by meteorological information, which is also available very dense level. We are able to calculate, and this is aggregated here. On the one side, these are the blue and the green lines. We are able to calculate the soil moisture, so how much water is in the soil and the different layers of the soil, and how the plants can use the soil. You see the little blue columns as the precipitation, and you see as the orange line, you see the crop water stress. So the model indicates whenever the plant tries to grow, but the soil moisture is below its level, so the crop goes to stress. And stress means less healthy and less biomass and less yield. We have here examples from 2 Austrian regions. In Upper Austria, you see we have in the winter, in the summer 2018, a very high crop water stress, while in Styria, it's the southern part in Austria, there is nothing like a stress. So here the plants can develop as normal. Yes, so the story is combining Earth observation, crop mapping, LAI observation with the model simulations, soil moisture, plant growth, water stress, and going in the model in the next level of the model. We can also calculate the crop water demand. Here it's in green, for example, how much millimeters, so same parameter like precipitation, how much water would be needed for perfect plant development. And out of that, we can simulate, or we simulated for 2018 for the different regions. For example, in Austria, this was especially done for publication, how much water is needed. And you see it for the different areas, that there's partly high level of water demand. So 100 millimeters is something that is, a real big rainfall or several days of rainfall. And also the model is providing information about how much yield is produced on the upper side if you're using only rainfall, and on the lowest image if we have irrigation available. And you see from the colors, especially for Styria, there's a significant difference between yield from natural rainfall and potential yield from if we have an irrigation. So these are 20 to 40% of tons per hectare that is giving the difference. And such simulations about yield is something that Vista is doing also in a commercial service. In this commercial service, we are going to a higher resolution. So this is 10 by 10 meters. And so this is directly not, also this is not for a region. So this is directly to specific farms where we can retrieve the crop water demand for the different crops, soybean, corn, winter barley, and for different years. And you see there's a day-by-day variance in the crop water demand, and of course also in the what kind of plant is there. And here we come to the beginning. Knowing the crops in detail is important for all that. All right, so that's the story on how big data and all the data activities can lead to services for farmers, for regions, and for farmers. We're doing that in the project also for farms in the different areas. And you see there are more specific, highly detailed products from our Talking Field service, for example, available. So this is not all that was developed in ExtremeEarth, but it fits together what is practice and what is extended. And yeah, this is very detailed. 1 minute about the Duero River Basin, where we run the model in a lower resolution. So we have the whole catchment detailedly modeled, and we are analyzing seasonal forecasts and the water stress and the irrigation water demand for the whole catchment. And we're also doing analysis on how different forecast scenarios from Copernicus have an effect on knowing beforehand what's the need on irrigation of water. So final slide here is again the blocks going from the Copernicus data layer to the ICT layer, the food security tab, the different project activities, AI training, what Trento did, the HOPSWorks, what Logical Clocks does, Sentinel-2 services, what Vista does, the water and land modeling also from Vista, leading to the crop information, leading to the water availability and the irrigation information, and the 2 catchments where we applied it. On the right side, you see our websites. Earth Analytics is from the ExtremeEarth project. The food security tab has a website, and of course, Vista Geo has a project or has a web page. So that was my contribution here. I think I'm more or less in time. So thank you for your attention. I don't see you out there in Europe or in the world. And I think we will go to questions later on. And I'm stopping here and hand over, I guess, to my colleague, Nick.
Thank you, Florian. My name's Nick Hughes. I'm the leader of the ice service at the Norwegian Meteorological Institute, and I'm based in Tromsø. I'll be talking about the polar use case in ExtremeEarth. I'd like to thank I've got a few people who have assisted with this presentation: Alistair Everett, Andrew Fleming, William Copeland, and David Arthurs. And in the polar use case, we've had a number of different institutes involved: University of Tromsø, German Aerospace Centre, Polar View, and British Antarctic Survey. The presentation will cover a quick introduction to the polar use case. I'll explain a bit about the polar thematic evaluation platform, some of the workflows we developed in ExtremeEarth, and then how we plan to exploit some of these results. The polar regions, they play a critical role in regulating the Earth's climate and ecological systems. They're also one of the areas which are experiencing significant change, so-called Arctic amplification. And that's led to increasing social economic activity. There's more people wanting to sail vessels through the area, the Northern Sea Route and Northwest Passage. And that's leading to greater interest both politically and economically. With that, you're seeing increased risks of potential accidents, and those would have major costs, both for the environment and in terms of the cost of actually cleaning up the results. The International Maritime Organization has now set up a polar code to cover the use of these areas. And this requires that ships have up-to-date information on sea ice and iceberg information to promote safe navigation. To go back to the idea of the cost of an incident in the polar regions, the Selendang AU in 2004 cost $112 million to clean up. In 2018, over the Christmas holidays, a trawler ran aground in the Svalbard area. The salvage teams tried to recover it in the summer of 2019, but didn't take account of what were more severe ice conditions that summer, but then had to go back with improved ice information in the summer of 2020. And we're happy to do a full cleanup. The Polar Code encourages ships not to carry heavy fuel oil, but it's still not banned in the Arctic, even though there's a ban which has been implemented in the Antarctic. So providing improved information products, ExtremeEarth will help to minimize the risks and hopefully prevent some of these incidents taking place. The current state of the art is that we have expert manual interpretations of all the available satellite data. An ice analyst has to sit there during the day and take account of all different satellites coming in and draw the chart manually. This takes time, and the time they take to do it means that the information can be outdated, particularly in a very dynamic ice conditions. But you're looking at about a delay of around 3 to 6 hours. This is also labor intensive, so Norway is quite good in that we update nearly daily, at least every weekday. Other areas are less frequently covered. You go to other places in the Arctic and you only find charts of weekly at best. However, it's simple to interpret. You know that someone has looked at the available data and has made their best estimate as to what the conditions are, and there's no noise in the image. The environment we're dealing with is very complex. In terms of rather than different crop types and fields, we have all these different types of ice in different stages of development. You can see some examples here. And although the satellite information we're getting is also based on radar, so because there's a lot of cloud cover during the winter period at the moment, it's permanently dark up in the Arctic. You can't use an optical satellite like Sentinel-2 to view it. You have to use a radar imager. And that brings with it further challenges in interpreting the image and making the best decision as to what it's representing. We've looked at the user requirements coming from a number of different projects, Copernicus itself, the Kepler project, Siderus, and the International Ice Charting Working Group. And in addition, ExtremeEarth ran a workshop at the start of the project where we invited users and stakeholders to participate and provide their needs and requirements. What we found was that high resolution products are necessary. 95% of users want something which is better than 1 kilometers resolution, and 87% of those want something which is better than 300 meters resolution at the moment. And at the moment, things like the Copernicus Marine Service work on scales of 1 kilometer or worse. So their typical product is around sort of 5 to 10 kilometers. There's a preference for more frequent updates. 79% of users want near real time, so within 24 hours. However, only 7.4% of those saw a need for quasi-real time, so less than 3 hours. Most, 44.2%, were looking for updates between 3 and 12 hours. So there could be some slight delay, and that can be accounted for in the delay in getting the image data from the satellites and then processing it on the ground. There's a number of different requirements in terms of different parameters needed. Sea ice edge, iceberg location, and sea ice type were seen as the most valuable ones which could be delivered. The format, as well as images, there's particular specialized data formats. So S411 here is the use it in electronic navigational chart systems. You can then put your navigation on top of that and see how that relates to the ice conditions. And yeah, spatial resolution, temporal information I just mentioned. And why is it difficult to do this? As I said, the optical images are frequently obscured by clouds and darkness. So this is a kind of typical type of image, or at least it's a fairly good image because you've actually got some gaps in the cloud. The synthetic capture radar satellite Sentinel-1 is unaffected by cloud cover. You get more detail on the ice surface, but the interpretation is a lot more complex. This is because of the interaction of the radar with the ice. The different types of sea ice have varying levels of salinity, and these get reflected in terms of the amount of radar signal you get back to the satellite, and that varies according to the time of year and the temperature as well. So what you see here is on the left is a sea ice in a winter situation from the radar, compared with the same sea ice in the summer. This was what we call landfast ice. So we know that the ice didn't move between the two images. And you can see there's a vast difference between the quality of the two images. The image on the right is a lot darker because you're getting a lot less signal back to the satellite, and that's due to water on the ice surface. You can see that the what was the brightest ice class, the rough older ice on the left, becomes one of the darkest ice classes on the right. And this provides lots of challenges, both for human and for automated computerized interpretation. Unlike the food security use case, our equivalent of fields of crops, ice flows, are constantly moving. You can see an example here from a meteorological satellite just showing the ice drift. And when you have very dynamic conditions, it makes it very difficult to track the same ice from place to place. It's very difficult to build up a time series of the ice conditions and how they're changing over a seasonal cycle. I'll talk now a bit about the Polar Phonetic Exploitation platform. Like the food security one, this is a shared virtual environment for finding and using Earth observation data. It provides computing power, all the data, storage, and analysis tools. And it's part of a series of these platforms developed by European Space Agency to help users handle the vast growth in volume and complexity of Earth observation data. And what we've been doing in ExtremeEarth is extending the functionality of this to support the polar use case. This is a schematic just showing the different levels and different parts of the Polar Phonetic Evaluation platform and how it fits into the European Earth observation system. So how it links into the people generating the data, European Space Agency, Copernicus, which is, I guess, the European Commission, and EUMETSAT, who generate data. You then have the DSs and various commercial and national ground segments and different missions. And then at the platform level, things like Polar TEP, Open Earth Engine, and Probe-V. On top of that, you have the various users trying to do that, scientists trying to exploit the data, public sector trying to analyze the results, and then industry as well trying to understand how it applies to them. So the Polar TEP has now been integrated with the CREO-DS, the Data and Information Access Service. And it provides access to the Copernicus Sentinel satellite data and information platform from information products from the different Copernicus services, such as the Copernicus Marine Service. It hosts a number of training data sets. There's a number here: AI for Arctic project and ASIP, a Danish project. They have various sea ice classification routines, and then also the polar use case training data we developed here in ExtremeEarth. It provides scalable processing resources, so you can set up batch jobs and triggered processing. So if you know a satellite, you can set it up to alert, or at least start processing if a particular satellite image comes through, covering a particular area. And it has provision for sponsored use of commercial platforms from the ESA network of resources. In the polar use case, it provided a number of customized user virtual machines. There was integration of the HOPSWorks and Strabon capabilities, which were mentioned earlier. There's various setups to adjust for computer security, getting access through firewalls to different institute sites. As mentioned, we had CREO-DS and Copernicus data access. There was GPU support for improved processing speeds, and support for setting up automated reinstallation of the cluster setup. The data could be integrated through the object store, and then once you developed a processor or data processor, you could then publish it and make it available to other users if needed. This shows how it fitted in within the ExtremeEarth project. We had it brings in the artificial intelligence, which is developed in other work packages, and the Copernicus EO data, links them together, and then provides the outputs out to the different users. And we focused here on mapping of sea ice type and icebergs at high resolution, spatial resolution. The processors were integrated by having developed the model with the training data and the algorithms on HOPSWorks. This could be exported to a disk file and then used to construct a Docker container, and that could then be put onto the Polar TEP, and then published out into a processor and used through the Polar TEP web interface. This is an example of what the web interface looks like. You can see here some images, examples showing some images which came in over the Greenland Sea area and Svalbard. In the map on the left, these are listed as granules in the kind of middle column there, bottom of the middle column there. And then you can see it on top right here, you can see the different processes which could be applied. So you can choose those and then customize the settings on those to get results according to how you wanted to process it. This gives an example of some of the process status information you get from the system. This shows you the different jobs which have been run, and then whether they succeeded, or sometimes you can see whether they failed, or you get some information as to whether they're ongoing. You can present here some of the workflows we went through. First of all, we developed a number of different training data sets. Met Norway developed a number around the East Greenland, Denmark's Haven area. That focused on fast ice because it wasn't moving. We could look at the seasonal variations in the what we're seeing in Sentinel-1 images. That covered sea ice concentration, form, ice type, and also icebergs. University of Tromsø looked at an area north of Svalbard, and that had a number of different ice types derived from Sentinel-1 images. And German Aerospace Center developed two different data sets based on Sentinel-1. This was looking at different patches of different sizes. These were classified into 8 different classes using kind of interactive, active learning on their system to bring in expert knowledge into their classification. With all the activity in the polar use case, we also came up with a number of different algorithms. University of Tromsø came up with some supervised algorithms, that ad hoc, FCN8 and VGG16. They also came up with some semi-supervised algorithms, modified VGG16 with label propagation, and then a deep 16 layer architecture. And then in the German Aerospace Center, they were using latent Dirichlet allocation from data mining and active learning as well. At Met, we worked more on the implementation side. We trained the model on Hopsworks, and then to avoid network overheads, exported the model to disk, and then tried to copy it over into the Creadeus architecture. This Docker container, which is then developed, can then be run also on the internal infrastructure at Met on our own computer facilities. And then for other intermediate users, this is how they'll see be able to work with the PolarTep and the Hopsworks system in Creadeus. Model trained on the system will be able to export it to disk and then put into the Docker container. That will generate also a JSON file, which can then be used onto the PolarTep. The PolarTep will process the development, will then be able to feed through into the PolarTep web interface and publish there. These can be developed on any machine, for example, a laptop. And for ExtremeEarth, all the pre-processing, post-handling, and import-export has been done using the Sentinel-1 toolbox and Python, which are now running within can now run within a Docker container on the PolarTep platform. So what we typically see is the user will be able to ask to process the satellite images with a particular processor. The results can then be made available on the PolarTep portal, either through the map, or you can set it up to provide you with a download link. At the moment, the demonstrations are not using GPUs, and that will be something which will be worked on in the future. This just shows one example, a classified image run through the PolarTep, providing an output map, which has then been accessed through Quantum GIS. And the format of this is the Beam DMAP format, which comes typically used by the ESA Sentinel-1 toolbox. So what the advantage of these different maps in terms of providing high resolution, particularly at the full satellite image resolution, is that we have much more high resolution mapping. This can be used operationally for tactical, strategic, and short-term planning. With the build-up of routine processing of these data, we can then be used for more sort of longer term things like climate model development and for looking at the historical occurrence of sea ice for navigational planning. And there's further work being done for the within science community publishing on some of these results. So we'll see a number of journal articles coming out in the future based on the ExtremeEarth data sets. So yes, ExtremeEarth has had a significant impact on polar communities and will have a legacy beyond the life of the project. We've developed a lot of new capabilities in the polar TEP, and we've also had a lot of work within the polar machine learning community, setting up workshops and continuing those through things like ESA Phi Week in some of those projects. I think that's all I can say here for the polar use case, and I guess we can hand it back to Manolis for, I guess, questions and stuff from the participants. Thank you.
Thank you so much, Nick. Thank you so much, Florian. I think we are actually 15 minutes late because we overshoot our time. So no questions. There are no questions. So I apologize from the three of us regarding this delay. It was due to a misunderstanding, and we can leave the floor to the next session. Thank you so much for attending, and don't forget to join our online workshop. Thank you very much and have a nice day.